short intro. So can you hear me? Swapan, shall we start?
It's up to you entirely. I'm ready.
But I can still see that people are walking in.
I'm glad Tarun could make it.
Yeah,
So,
just about made it. Okay, so I think we can start and then hopefully
turn off
people...
your cell phone, Tarun, so you don't get called off. Turn off your cell phone.
Turn off your cell phone, yeah, indeed. So it gives me great pleasure to welcome our colloquium speaker for today, Swapan Chattopadhyay. Swapan Chattopadhyay is a particle physicist with contributions to innovative high-energy particle colliders, exotic light sources, and lasers based on free electrons, and ultra-fast sciences, for which he received the Berkeley Holbach Prize. He is Emeritus Sir John Cockcroft Professor of Physics in the UK and Distinguished Scientist Emeritus with global affiliations at CERN, which is of course in Geneva, Switzerland, Fermilab in the USA, University of California, Berkeley, also in the USA, and Stanford University, also in the USA. Pretty close to each other, the last few affiliations. Currently, he's spending autumn 2022 in Bangalore as Infosys Chair, visiting professor at IISc, and Adjunct Professor of TIFR, ICTS. Following BSc and MSc degrees from St. Xavier's College, Calcutta, and IIT Kharagpur, respectively, he completed his PhD in physics from University of California, Berkeley, and postdoctoral research at CERN. He's a fellow of the American Physical Society, the AAAS US, IOP UK, Royal Society of Arts UK, and corresponding fellow of the Royal Society of Edinburgh, UK. So with that, I would like to give the floor to Swapan, who's going to talk to us about quantum sensors in cosmic archaeology and electron-photon entanglement. Very rarely do we see a title which has so many of the interesting areas covered. So please.
Thank you, Urvashi. Thank you. I'm going to speak from this side because that's very constraining for me, so if you don't mind. And so what Urvashi did not tell you is that I was going to quiz you about this picture. Can any one of you recognize what? This is where I grew up until the age of 13. And then when this India-China conflict started, and Dalai Lama fled and all that. So then my parents came back to Calcutta. I realized that they are actually not from Darjeeling, they are from Calcutta, which was a busy, crowded city. So I just finished my 4 years of high school, went to college, fled to Kharagpur to do my master's, and went to California to do my PhD. But I had a fantastic childhood there. I learned mountaineering, took lessons from Tenzing Norgay and Edmund Hillary, who came to the Himalayan Mountaineering Institute, which was founded by New Zealand and Government of India. And these two gentlemen wanted to give courses to people. Only 6 little kinder signed up. All the adults were scared to take a class from the Tenzing Norgay and Edmund Hillary. The second thing is I actually spotted Sputnik in the sky with bare eyes. You could see this thing moving around the sky. Fantastic childhood. Okay, so let me just thank, first of all, Tarun for hosting me here today. And I hopefully will get a chance to talk a few minutes afterwards. I know you have a busy schedule. Then I want to thank Urvashi for actually inviting me to give this colloquium. And I'm going to talk about things that has many of my colleagues, I call them my quantum colleagues, qubits, cavity qubits, atom interferometry, and particle beam physicists, as they've, throughout my career, learned a lot from them. So I give them my thanks. So I have a lot to say, and I hope I can finish in time. I put probably too many slides on atom interferometry for dark sector search because I hope that Tarun would be here. So I will tell him a little bit about gravitational wave detection. But let me see how it goes. I do want to get to this last topic, which is very fascinating, quantum topic, which RRI people would be interested in. But okay, let us see how it. So I'll talk a little bit about sensors, a little bit about boilerplate thing. Don't be insulted if I say something that I constantly say these things to myself. And then I should tell you a little bit about the status of particle physics because many of you probably are not quite at the forefront of particle physics. So I will tell you a little bit where it stands and why we are turning to quantum sensors beyond accelerators a little bit. And then that's where I tell you why you want to look into this. Then I give you just 2 examples of using quantum sensors. A qubit inside a superconducting cavity, and you entangle an entire macroscopic electromagnetic field inside a superconducting cavity with a qubit. And you want to measure very exotic particles like dark matter particles and so on. And the second one is atomic interferometry as a probe of both the dark matter as well as very early primordial gravitational wave fluctuations from the Big Bang. And then I talk about the totally different topic, but we have been able to catch a single electron, store them in a ring for 5 to 6 minutes and see the light coming out of it and trying to understand the quantum entanglement of the light and the electron from a single charge. So it's a Feynman vortex, but it's a very complicated. It's not just a point vortex, a lot of dynamics going on. Feynman is of no help in explaining that vortex. So, okay, so just don't be insulted, but I always tell myself that we came into this business, started with Galileo, who said that if there's something there that is measurable, you think with your instruments in the lab, please go ahead and measure it and then try to fit it with your model of the world. And if you don't have something that you don't think is measurable, try to make it measurable and then measure it so that you can actually have a ontology of how the world works. And this was actually then echoed 200 years later by this gentleman that you need instruments to actually measure. And so he said nothing tends to advance knowledge as the application of new instruments. Of course, you need theoreticians. I noticed there are not that many theoreticians at RRI. You probably need a few more. But you need theoreticians to play hand in hand with experimentalists to actually make progress. So, right, so there is this telescope. This guy, Galileo, was very smart. He's trying to butter up the royalty to get more money for the next telescope. And he always had the lens grinder see what he sees through the telescope. And he gets excited. He said, look, I've saved 10% of what I get from the king. So you could grind me a bigger lens. And of course, he would grind it because then he can see through the lens to see what more he could see. So it's a collaboration between scientists and the technologists and engineers who enable instruments that we use all the time. Okay, and then of course Newton, so on. So there are all these instruments of I've been interacting with large lasers, even laboratory lasers, which are quite large. And you take a femtosecond laser in the lab, that turns out to be quite large. Telescopes, satellites, microwave, radio telescopes. And then you have these complementary things that you are very familiar with here, these laboratory scale sensors, which actually can give you very precise information about this. So I'll talk about why we need to go to quantum sensors in a little bit. But in my main field where I actually got my hand made expert into it was this, beginning with the cyclotron in 1932 to today. We have this 27-kilometer huge ring. It took our 100 years, 1920s to 2020, to actually establish the model of particle physics. So the latest in that chain was this particle called the Higgs boson, which presumably closes the model, and I'll show you what that is. I got Nobel Prize and all that. Of course, it was headline news, but you realize throughout this 100 years, many scientists, theorists, experimentalists, engineers, students, postdocs, technicians, they all work together to actually bring this model. And basically, it's simply said, in simplest form, we just have now, I call it a mandala because in Tibetan, Nepalese, Sikkimese, and Buddhist Darjeeling, I used to see beautiful mandalas. So basically, there are 6 quarks, up, down, charm, strange, top, bottom. There are about 3 electron-like particles, electrons, slightly heavier electrons, muon, tau, 3 very funny particles, neutrinos. They hardly have any mass. And then there is 4 particles, but they're more like fields, photons, then the W and Z, which make radioactivity work, weak interaction. Then there is this gluon, which makes things bind together in the nucleus. And then squarely in the middle sits this new particle that was just discovered in 2012 called the Higgs, which supposedly gives the meaning to a substance of a particle. A particle is there, it has a mass. Mass is this kind of gravity. It is what it is. So what makes up that mass? Apparently, you need this particle to explain how mass is generated in other particles. So there you have it, the 17. Of course, it's not so simple. There are 2 types of W. There's 8 types of gluons. Every particle has an antiparticle and so on. So it's like a 50 or so particles. But this is basically simple. You can even make a high school student remember. And that is what we understand ordinary matter that we see around us to be made up of. Okay. Basically, you can understand almost everything except 2, this Higgs and this neutrino. So just let me tell you a little bit. These 2, the Higgs is a very funny particle. We just discovered it. We know it is important and sits in the middle of this mandala, and it gives meaning to everything else. But it sits in the energy landscape of the rest of the particles very precariously. Its stability, its self-coupling, its decay, we don't know much about it. And the other particle is neutrino. This neutrino is a very shy particle. It's always playing a kabuki game with you. It does not want to reveal its identity. You catch it here, you see it one face. You catch it, same neutrino, there it gives you a different face. You catch it there, so it's a different face. So it comes in 3 flavors, and it's constantly playing flavor oscillation game. And we don't know why. They have 3 different masses, very tiny. But so people are trying to understand the neutrinos by, oh, let me just, one slide got deleted. Let me see. Oh, yeah, one slide got deleted here. Neutrinos, people are trying to understand from having deep underground detectors and seeing neutrinos coming from the cosmic rays, or producing them in a large accelerator and sending them long distances like 2,000 kilometers, and you try to catch them as they propagate to see their kabuki game and so on. And for the Higgs, they're proposing a preposterous 100-kilometer circumference proton-proton collider in Geneva and in Beijing and so on. I'm not so sure whether these things will ever come to be, but we are not being smart enough to know how to study these 2 particles in any other way. But now let me turn to the other side of it. After 40 years of doing all this and establishing this beautiful model, cosmologists are telling us that when you look at the universe and you know it's expanding, and you kind of go back and you see 13.8 billion years ago, something very special, crazy must have happened. So energy density was very high, and space and time, everything was probably emerging from the special event. But in order to make sense of the structure of the universe, the way we see it and the way it's expanding, you need to postulate 96% of the mass and energy of the universe to be dark, outside of this 4% of this, what I talked about, the standard model. Ordinary matter that you see is only 4%. 21% is dark matter. It has gravitationally active. It interacts with everything else gravitationally, but not electrically, not magnetically, not strong or weak interaction-wise. And then 70%, 75% dark energy, which actually is responsible for the actual acceleration of growth of the universe, so on. So 96% is dark, and a lot of that probably happened in this area. And I've shown here symbolically that because space-time was emerging, just like the universe was very hot, and we know now we are cooled down by looking at the microwave background on the antenna, and you know it is today something like 2.7 degrees Kelvin temperature, and it's still cooling down. Similarly, there was probably a lot of tremor of the space-time metric, because you are creating matter and energy at this Big Bang. So there's probably some kind of a mini quake. Those tremors are probably still here as a background, cosmological gravitational wave background, just like cosmological microwave background. And understanding the nature of that radiation, their power spectrum, and their strength can actually help you to discriminate between different models of how the universe came to be. Did it start from a Big Bang and growing, asymptotes to something, or did it crunch into something, then bounce back, or is it going to grow and then bounce back? So the gravitational wave that you generate at that point has a very different spectrum and strength. So if you could measure it directly, then you can tell a lot about the beginning of the universe. So a lot of the sensors that we are looking at today is to look at dark matter, dark energy, and early gravitational wave. Now let me go back to the very beginning. You know, if you go really back, there's no reason to believe that this expansion did not really start from very, very small, like 10 to the minus 41 or 42 centimeter kind of a thing, where the entire world was in a Planck scale. And then, of course, today we are all, everything was entangled in this Planck scale little thing that we call the universe. Today, 13.8 billion years later, the sun, the moon, the galaxy, you, me, everything. But that quantum entanglement from that Planck scale, in principle, should exist even between then and now. But of course, in the process, a lot of external disturbances and interactions which destroy the nature of the quantum coherence. So it probably going to be very, very hard to see that kind of a, but in principle, the entire world can be described by entangled wave function. But a byproduct of that is that probably a lot of the secrets of dark matter and dark energy are out there, and you do not have to really create them in a laboratory like in big accelerator to find them. You have to be very smart to devise very, very sensitive and patient detectors that can detect the remnants of dark energy, dark matter, and primordial gravitational waves. So let me give you, as an experimentalist, I will give you some numbers. So people say the universe is expanding and expanding even faster than what we thought. That means as it grows, its energy density is being collected with the size of the growth. And if you look at the actual density, 6.3 times 10 to the minus 10 joules per meter cubed, which is the energy density of dark energy, if the cosmological observations are right. So this unit is the same as pressure, newtons per meter squared, same as joules per meter cubed. So if you look at the Casimir force, the force between two plates in vacuum due to quantum fluctuations, or if you look at a cold cathode ionization gauge that you always use in accelerators and particle beams and stuff, these are actually comparable numbers. And we even have an experiment at Berkeley undergraduate lab where we measure this kind of pressure by squid magnetometer detectors and stuff. And if you look at dark matter, it's slightly higher. It's actually 4 orders of magnitude higher. So this is the kind of scale of things. They are not that small numbers, but if they're fixed, like if there is a cosmological constant that tells you that you have this kind of energy density, then unless there's some fluctuations on it, you cannot really measure a DC thing that easily. A DC thing simply sets a bias, and you measure everything above it. But if there's a fluctuation of the DC bias, in nature, nothing is fixed. Then, of course, you have a chance of looking AC effects of that bias. So we are looking into whether we could detect fluctuations of field. If this energy was electromagnetic, it is not. But if you pretend this energy is electromagnetic, and it converts into, if you had an electric field in free space of 12 volts per meter, you put a battery of 12 volts across a meter, you get an electric field, and square that, E squared, over 8 pi or 4 pi, whatever, you get this kind of a field energy. So it's 12 volts per meter. It's really not that big, not that small and not that big. And if it fluctuates, we should be able to detect it. But of course, it's not electromagnetic. It's dark energy. So we have to have different kind of sensor for it. So now let me just give you a little lecture on quantum sensors. Time just flies. So these are instruments that are not just quantum in nature, meaning photoelectrons or depending on quantum mechanics, but if your output is always volts, currents, counting photons and so on, but if your basic mechanism has in it superposition and entanglement of quantum nature, then that becomes a quantum sensor, which actually has much higher resolution than a typical classical sensor. Let me give you an example of that. I just explained it very simply. Any kind of a quantum screening, quantum impulse, it has a back reaction, has a recoil, and I'll give you some examples of the amount. No, can I suggest that I give to the talk, and you just keep it in your brain, and then you come back. We have a lot to, yeah. I have so many questions, I can bet you that you. So if you imagine a back recoil, you actually get it's a number. Depending on the mass and the frequency you are looking at, you can get a sizable or not so sizable back reaction. But there are many ways to beat this kind of a zero-point noise by squeezing techniques, state transport, single photon detectors. Okay, things like that. Okay, so let me give you an example of that we actually use. So if we can do that, then there's a lot of applications in this dark matter detection, electric dipole moment detection, ultralight dark matter, new forces, new particles, and so on. I explained this in a way that quantum mechanics allows us to create squeeze states. And if you can somehow couple the variable that you are interested in physically to know very, very precisely with a variable that you don't really care about, but you kind of couple them, superpose them, entangle them, they are not independent quantities. You can squeeze information into one of them and scatter the unnecessary information in the other degrees of freedom. And then actually you can get infinite resolution if you can squeeze infinitely tightly. One example of that is actually, if you look at just the radio wave, has a sine and cosine, or amplitude and phase, and of course it has a footprint, and it has a minimum volume. You would say thermal noise would give you half kT per resolved mode, and quantum noise always leaves one photon from the amplifier that gives it. So you are still left with this noise even if you go to the t equal to 0 limit. So there is a limit to how good you can make these things. But if you can squeeze this squeezing technique, you can scatter in phase by creating an interaction that does not change the amplitude. So you create an interaction mechanism that preserves the number operator. So it preserves the number operator. So we do not have to destroy a photon in order to measure a photon. So this is called quantum non-demolition technique, and a lot of people worked on it, got Nobel Prizes and stuff. So if by this technique, if I just give you a number, if you simply look at noise rate in a simple system versus frequency, okay, this dashed line is a single quantum limit. The red line is at this technique operating at 2 Kelvin, the purple line operating at 100 millikelvin, the blue line operating at 30 millikelvin. And you see at this position, you are already below the quantum limit, so you are simply limited by the temperature. So as you reduce the temperature to 0, you get very, very good noise. So quantum, you are not limited by quantum noise. This is actually very huge in cavity qubit technique, and I'll just tell you about that later on. So now let me give you 2 quick examples of application of quantum sensing. One is a cavity qubit sensor for dark matter detection. Other one is atom interferometry to detect both dark matter and gravitational waves coming from the Big Bang. A cavity qubit actually is a very good example to detect axions or hidden sector photons or all kinds of stuff. So physicists are split into 2 camps. Astrophysicists, cosmologists believe that the dark matter could be a bunch of 60 solar mass type black holes hiding here and there. It could be an astrophysical phenomena. Particle physicists believe it's a particle, a whole bunch of new particles that are adding mass. And then there are 2 camps. One camp says there must be very massive particles but very weakly interacting, so they are called WIMPs. We could have seen them in the Large Hadron Collider at CERN, but we are not seeing any hint of any of these weakly interactive massive particles. The other camp said that maybe they're very light, like sub-eV, milli-electron volt, micro-electron volt, almost wave-like entities, fields. They're particles, but they're fields, like dark light, ultralight dark matter, axions, dilatons, or like hidden sector. For every photon you see, there is a photon in the dark sector, and so on. So that's the thing that you can actually sense with quantum sensors. I'm going to give you an example of this kind of a thing. So here is an example that if you have a very precisely tuned antenna circuit inside a totally electromagnetically shielded volume, a cavity. And let us say that you have ordinary matter coming in. It cannot go in because you've shielded it against ordinary radiation, so it gets scattered, does not enter. A dark matter does not interact with ordinary matter like neutrino. It just goes in, and it will go, and all of a sudden, inside a hollow cavity, where there is no photon bouncing around, you see a photon appearing from nowhere. So you have to make sure that that photon is not a noise photon from your electronics, but it's a genuine photon coming from nature. And so the whole trick is to have a device that detects a photon that you should not be seeing otherwise, but it is coming in. So that's a detection of the photon. So people typically put a qubit. Qubit is a two-level system. It could be two-level atom. But here it's a two-level Josephson junction, a superconducting Josephson junction, and it can only exist in two states. And you can actually write this object interacting with a cavity. Cavity has creation and destruction operators of the photons with a little frequency here, and you here have a little qubit, two-level qubit, and actually you have a coupling of the qubit with the field of the cavity. So this is a coupling, and actually you can look at the cavity-qubit coupling G. This object is a separation of the tuning of the cavity from the qubit, and it's called detuning. And of course, anything you do, you can imagine either the cavity is torque shifted by the qubit, or the qubit is torque shifted by the cavity, depending on how you look at it, because you can factorize, this thing. And let me just show you how it looks actually. So you can design the qubit in a way that you actually have shifts due to the fields. Torque shift is bigger than the mode bandwidth. So there's a very particular constraint on how you design these qubits. And then actually you have to look at the modes. Cavity has a whole set of electromagnetic modes. The bigger the cavity, the higher the density of electromagnetic modes. But then, of course, the frequency of the fundamental is very low. So you have to balance between what do you think is the mass of the dark sector particle, which is directly related to the frequency of the cavity that it will resonate, and its higher order modes. So if you start out with a very low frequency cavity, higher order modes, but there's a cutoff at some point, so you'll get a bandwidth, which is, you may find something, you may not, or you get many, many small volume cavities. So you increase the volume by a large number of cavities, but each cavity is very high frequency. So you get a many, many high frequency. So that's a balance between the two. And so people are designing these cavities in a very careful way, looking at the Stark shifts and whether you can resolve this shift. This is a qubit, it's Stark shifted by the cavity. So you can look at this way, factorize the spin of the qubit. Or you can look at the cavities Stark shifted by the qubit. Overall, you actually have to eventually make sure that the entire electromagnetic field, it rings for a long enough time to be able to register as an interaction with the superconducting qubit. So normally if you take a cavity, aluminum or copper, it has a very broad resonance, Q, which is the bandwidth divided by the frequency, typically 10 to the 3 or 10 to the minus 3 or 10 to the minus 4. So here, these cavities can be superconducting cavities, so they have a Q of 10 to the minus 10, minus 11, minus 12. So if you imagine two cavities, one is 10 to the minus 11, one is 10 to the minus 11, the two of them is 10 to the minus 12, and the probability of finding a dark matter particle is 1 part in 10 to the 24. So you already got 10 to the 22 from the two cavities, and all you need to do is to now get above factor of 10 to the 2 by electronics, cryogenic things, all of that. So it becomes easier in that way. So when you actually look at what is your projected discovery potential in terms of axions, you can discover coupling and their mass. You span a wide platform here. You either see it or you don't. If you see it, great, you get a Nobel Prize. If you don't see it, you set a boundary saying it cannot be above that, below that mass, or above that mass. So it's called a threshold calculation. So with this in mind, many experiments are being funded. I give you one example of, somebody knows David Schuster here. I think it's Anton, you know David Schuster, yeah? David Schuster makes these qubits that you make. And here is Conrad from Colorado, and there are two from Fermilab. So we use this cavity, superconducting cavity, 10 to the 11 Q, and we use this qubits made at the University of Chicago, and we actually use this technique of quantum non-demolition technique to actually make sure that the signal is a genuine photon signal, not a noise photon signal from the amplifier or the electronics, okay? Okay, so let me just take a pause here, and let me now quickly tell you about this thing, and I have too many slides on this, but so now atomic beam, you know, LIGO discovered coherent gravitational waves coming from black hole mergers. So those are coherent waves, huge waves, and they keep their phase as they propagate from here, then you detect it here, the same wave, and you know, you correlate the two, and you have seen a gravitational wave. The gravitational wave from the Big Bang is supposed to be stochastic in nature, so it's a random field, and you have to measure correlations of that field, and it is much, much lower intensity probably, because they are coming from fluctuations of space-time through inflation or some other mechanism at Big Bang. But it is also true that if you use atoms instead of mirrors, LIGO uses mirrors, and a gravitational wave is going by, so the mirrors oscillate. And mirrors are suspended, they are supported on Earth. Earth has, you know, all kinds of motion. So below 10 hertz, it becomes difficult to isolate these mirrors. But if you have a freely falling atom, it is not stuck to the ground, it's freely falling. So there is no limit to the frequency structure to its response. But if you use atoms, you can also be sensitive to the atomic transition lines. If the dark sector, like dark photon or dark matter, interacts with the electromagnetic photon, then the line, the transition lines would have an oscillation in them. So atomic transitions would not be given by a known constant alpha. They will fluctuate with time, because alpha is fluctuating by interacting with dark matter. So you detect by atomic interferometry both dark matter and a gravitational wave. Let me show you that. So we are looking at anywhere between 10 to the minus 23, 10 to the minus 21, 10 to the minus 25 kind of strain, delta L over L, at about 1 hertz kind of a thing. So let me explain to you how it couples to the atom first. You can just simply look at a typical particle physics Lagrangian, and the dark matter is simply this field. If it's, imagine the density of dark matter is given by rho, then the field amplitude is square root of the density. That's sensible. You can imagine some kind of a wave, low energy, wave-like particle, which is an axion or a dark matter particle. And if you look at it, do the calculation, you'll actually see a fluctuation of the ground state and the excited state. And that is when the ordinary matter interacts with the dark sector. And people have estimated how much fluctuation you get at what frequency, a lot of papers on it. And in the gravitational wave side, I would say that LIGO cannot really go down below 10 hertz. And LISA, which is space, it starts out at very long wavelengths. So in between, there is kind of a gap. It's called a mid-gap, and this is where there could be astrophysical objects that give you gravitational waves, or there could be, people are calculating what would be the frequency of gravitational waves from Big Bang that you would see, and many people are projecting that it could be in this little bandwidth. So this mid-band is very important, and atomic spectral interferometry very sensitive to this frequency band. So let me give you a quick example of, if you take a LIGO, you have two masses, light goes through, you have also a quadrupolar wave, breathing wave is going through, so you will see two masses going up and down. And of course, the strain you want to measure in a LIGO, suspended end mirrors, and you do laser interferometry, and you take the perpendicular arm to be your reference, which is not oscillating. So that's your reference. In atomic interferometry, freely falling atoms are the mirrors. The time of flight between the atomic clouds and the laser is your interferometry, and atomic phase of the atom is the clock. So you don't need a transverse reference line. You use the clock itself as your reference. And so instead of light fringes, you will get atomic interferometer fringes, because an atom falling, imagine the wave function is a packet, but let's say it is e to the I k z. K is the momentum, which you can shift by hitting it with laser pulses. And z is the distance it's falling, typically proportional to time squared. If there's a wave going through, then z is not fixed. You think it's falling 1 meter, but it's falling 1 meter plus or minus 10 to the minus 21 meters. Now, if you can split the atom wave function into two, ground state and a slightly excited state, split them and then join them again, make them interfere, the two paths see two different phases due to the fluctuation of the path. And then you can see density of atoms at the bottom to have a modulation, which is atom interferometer, matter wave interferometry. So this is a basically simple example. You take an atom in a momentum state P, you split it by laser pulses into a pi over 2 pulse, and you split them into two. One goes far faster than the other, and then you let them propagate, generate some phase. Then you put a pi pulse to reflect them back, and then when you join them at the bottom, you see that the two have met together, but you have actually separated macroscopically the two superposed states, P and P plus a K, macroscopically here. So in the laboratory, people at Stanford have separated atoms in superposed states over half a meter, up to a meter, only for 10-meter drop. For a 100-meter drop, we can do 10-meter superposition and more. 1,000-meter gives you much more. So you can do macroscopic superposition. We are using, now I was talking to somebody here, we are using strontium atom because rubidium and all the other atoms people, atomic physicists typically use are good, but strontium is supposed to have more stability as a clock. So you're understanding a lot about the energy levels of strontium, and also is biased by the fact that at West Coast California, we have Stanford, Mark Tasevich has a little company, and he specializes in producing strontium sources. So we actually buy the strontium from him and understand it. And here is how the interferometer works, okay? So you have, imagine you have this system. You have atoms driven by the same laser, and this is your measurement baseline. Could be 10 meter, could be 100 meter, could be a kilometer, okay? Imagine an atom prepared in the ground state and excited state by sending a laser pulse, and you prepare them in the superposition of the two states, and then you drop them. And of course, when they drop, they have gathered some kind of a time that it takes to drop. So phase has advanced by that amount. But the time and the frequency, of course, are not constant, because the time of fall is not the same because a wave is going through. And omega A is also not constant because it's fluctuating due to interacting with dark matter. So what you have actually got here, delta T, an extra phase shift that's coming from the strain, gravitational strain, sampled by the atom, the length over C, okay, multiplied by omega A, which is also fluctuating. So you may think that laser already introduces a phase, but that phase is common because both clouds are being done by the same laser. There's a common mode rejection, okay? And so you are left with actually this object. Phase is omega A to L over C. So omega A is the dark matter contribution, HL is the gravitational wave contribution. And so it's very difficult eventually to separate the two, but we should get a signature of both combined into the atom interferometry, okay? So we have at Fermilab, we have a 100-meter shaft, and we have a 2-kilometer, 3-kilometer deep underground mine 2,000 kilometers away in South Dakota. So we wanted to do an extra 10 meter at Stanford to a kilometer. People will throw you out of the room. So we want to propose 10 kilometer is done at Stanford, 100 kilometer here, and 1,000 meter, 100 meter here, 1,000 meter here, and then you go to space for satellite-based atom interferometry. So this is a program. This is already funded. I'll show you the details. This is funded. This will be funded if this succeeds. And we already have a proposal for space through NASA and through European Space Agency to have contingent upon good scientific results on these two, we will have a satellite-based atom interferometry. So let me show you the typical. So it's typically, I explain this to high school kids, how the atoms are split and they are brought back together. And you do, this is a fountain, but you can also drop it simply without a fountain and so on. And you can look at the time frames that they fall. And so here is a shaft, kilometer shaft we have in the mine. So you can have 10 meter, 10 meter, 10 meter, many 10 meter interferometries, or you can have a one long 100 meter or 1,000 meter baseline interferometer and so on. So a lot of early explorations have taken place at this 100 meter shaft at Fermilab. I'll give you some pictures. It's a real experiment. So people have done all kinds of really take a look at the shaft. And it's a collaboration of Stanford, Johns Hopkins, Cambridge, Northwestern University, Northern Illinois, Fermilab, SLAC, Oxford, and Liverpool. And it's funded by Department of Energy, funded by the Moore Foundation, it's funded by the Kavli Foundation, and is funded by the UK Science and Technologies Facilities Council. So this is the program measuring a lot of in situ, the inertial noise, Newtonian noise, atmospheric noise, all the traffic going on the highway. So we are characterizing all the systematics of the Newtonian noise that could destroy your atomic phase. And once you study it, put it into your logbook, you know what to subtract when, night, day, diurnal variations and stuff, and then you can actually do it. The other thing we realized that it's not enough to have one interferometer, because we are moving to a galactic frame, and there is no reason to believe that dark matter or dark energy or gravitational concentration of waves is the same as you move along. So if you take two interferometers, initially you would think that the correlation would be 0. But if you just are patient and go long enough, observe, over time you will develop correlations of observations at one place with the observations at the other. So it makes sense to actually have another atomic interferometer at a distant place in continent like India, Europe, England or something. So we convinced our European colleagues. So there is going to be, this is America, in UK, Oxford, they got a European Research Council grant. So we are going to have a second one called AION. So these two are fundamentally going to study dark matter, dark energy, and so on. And eventually they also have found a kilometer-long mine shaft, and they also have proposed something to the European Space Agency to do. And there are other atomic interferometers. They are mainly geological, geophysical. China has a big project here. So, okay. And people have calculated sensitivities to dark matter, how low a dark matter mass you can detect, how strong a gravitational field you can detect. So there are these. So here, these are calculations, LIGO, advanced LIGO, LISA, this band gap. What can you do with a, in the laboratory atom interferometer? So these calculations are difficult. You can question them always because nobody understands how to really calculate a gravitational wave spectrum from Big Bang. It's not an easy thing to do. You assume inflation. Inflation may not be a real theory. It's just a conjecture. So, but these are just sort of projections of that. Okay. Okay. Now I have to talk about this because this is actually now changing here. Talking about, so we are learning a lot about these quantum sensors, but now we are beginning to understand a single electron photon entanglement, and this is essential to any kind of a photonic measurement. I gave a talk on this. This was published in Nature, that we have been able to cool stochastically a particle beam so that eventually you have only one electron left, very cold, and is going around in a ring, in a trap for 6-7 minutes, and then you see light coming out of it, published in Nature. And then I gave a talk last 2 weeks ago in ICTS, and so you can look in the YouTube that has more details on that. But what we want to do now is not published, but I'm going to describe it to you now. So we have this little ring, and we have used this stochastic cooling technique, which is in that paper in Nature from August. This paper describes how we do it. This was okay, and so we have actually been able to cool an electron beam and eventually let electrons drop off, and finally when you come to 2, 3, or 1 electron, we expand the potential well very quickly and trap a single electron in the ring. And this single electron goes, and you see the light coming out of it, and it lasts for about 6-7 minutes. That's an infinite amount of time for an experimental physicist to do something with it. So now, if you look at the light from this, this is the images of the cooled electron beam, and you can actually see on all 3 dimensions. You can cool. This is actually real-time images of the beam being cooled. But now what we're trying to see is light coming from the single electron. The 3 aspects which we want to study: statistics of the light, photon statistics, entanglement of the light and the electron, and a Cheshire cat charge exchange between electron and a positron. Electron and a positron are charged particles. That's why they emit radiation. A neutral particle doesn't. But if you look at radiation coming from a photon, you cannot tell whether it's coming from an electron or from a positron. But you know it's entangled with the charge. So if you can somehow, in the process of the light peeling off from the charges, they're still quantum mechanically entangled with the charge. You can swap the photon cloud by quantum mechanical interference, and then you have an electron with a positron's charge and a positron with an electron's charge. But how would you know that you have swapped it? Because there must be another yardstick to know this is an electron and that's a positron. So I'll tell you this one. So the statistics is basically a simple fact that alpha is only 1 over 137. So a single electron going around. And of course, you only see one photon every 100 or 150 or 200 turns. You do not know which turn you will see the photon. It could be the 39th turn. What's happening in the rest of the turns? You don't see a photon. Do you see an electric field, for example? Theoretically, you can actually create a electron-photon density matrix. You trace out the electron because you don't care. Electron, you get a density matrix of the photon. You trace out the photon, and you simply look at the field correlation, that even when you see the photon, do you still have a field left over? Okay. If I tell you an electron is going around a circle there, I'm standing 10 meters away. What do I see, and when do I see it? So I can give you statistics of how many photons I will see in a certain length of time, but I cannot tell you what electric field I will see, when I will see, what kind of fluctuation. Nobody tells me what, and Feynman cannot tell me that. So statistics-wise, there's a lot of information on what kind of statistics you can assign to photons. It's called a Fano factor. It's in a certain length of time, how many photons are coming, their variations and their average. If that ratio is 1, it's called a Poissonian light, and very common in lasers and radioactive decay. Or super Poissonian light, when it's bigger than 1, thermal light, or any classical fluctuation of light from incandescent lamp or so on. If it's less than 1, it's sub-Poissonian, probably a Fock state. When you look at both the electron and the photon, that statistics is not described by Glauber, Sudarshan state of a photon. A lot of complications due to quantum mechanics. I'm not going to, let me just skip that because of the sake of time. Okay. And basically then if you have a bunch of electrons, 50 or 100, then you only get one photon, and there is no predictability on your part about the fluctuation of the electric field that you will see. So we want to really probe deep into it and understand the statistics. That's the easiest part of the problem. The more important part is this thing. So this is a typical Feynman vortex, but actually, if you look at it, a lot of correlations in the process of emission. And if you just draw a simple hand-drawn picture, electron has charge, and semi-classically, that means there's a virtual quanta trapped inside the charge. That's why it is charged. You shake it off by shaking with a magnetic field, and the photon is trying to peel off. Initially, you have an electron, no light. Finally, you have an electron and a photon. But in between, you have really an entangled state of the photon and the electron. And this is really, you can mathematically describe it by bipartite distribution. So what happens is when you see the electron, you don't see the light. And when you see the light just coming out, you don't see the electron because it does not have any attribute anymore. It's given up all in the photon for a while until it draws energy from the vacuum to dress itself up as a fully charged electron. And then it can radiate again. So this little time, very short time, is the formation length of photon coming out of the electron and making the electron real again, okay? So you can now, why do we want to know this? It's because we really want to know the distinction between emission of light between the electron and the positron. This is the Cheshire cat phenomenon, that a particle has identity because you have spin, charge, mass, all of this, but probably you can peel off one of the attributes and separate the particle from the attribute and see if the identity is fundamental or it has a quantum mechanical Lila. So if you just imagine this as a thing that you have a cat with a green grin and a red grin, and somehow the cat is able to shed its characteristics of grin, and it can separate quantum mechanically, and you can somehow superpose the green grin on the red cat with the red grin, and the red grin is the cat with the green cat, then they have actually exchanged their grins. This has been actually written up by people. I'll show you the three papers by that. We are actually trying to see it in the domain of a fundamental elementary particle which has, let's say, a charge. Nobody knows what charge is. We just know how a charge behaves in a magnetic field. The nature of the charge we don't know. So imagine you have a positron, let's call it red cloud of photons around it, and electron, green clouds of photons around it. But you need to have another thing to tag, otherwise there's no distinction between the two. So it could be spin, but probably not good to use spin because spin is tied to magnetic field, and there's some other thing that you tag the electron, negative, and the positron, the positive. So you now shake the electrons like I showed you, single electron, you emit a photon, but you catch the electron in the act of emitting a photon, half emitted photon is still entangled with the electron, and you swap quantum mechanically the two clouds of photons which are nevertheless entangled with their charges. But then you superpose them at a later point, and you actually get an electron with a positron's charge and a positron with the electron's charge, and you know they are positron and electron because of this other tagging which you do not touch. In this thing, we can do this because we have now been able to store a single electron this way, and you can see the light. If you inject a positron, it will go the other way because the magnetic field is. So now we can have electron and a positron colliding in two different directions going on. We can bring them together in a very specialized chamber that can actually do this Cheshire cat charge exchange experiment by very special magnetic field. So allowing that cooling to a single charge helps us to do this experiment, which is very fascinating, I think. So I think you know that this gentleman Aronoff, same guy as Bohm-Aronoff effect, published in 2013. Then our Indian colleagues from HRI did some speculation, and the Chinese colleagues actually showed that two photons they have been able to do some amount of experimentation on this idea. Okay, so I think I'll just stop here and take questions. I've said a lot of things. There'll be a lot of questions, I know. So I wanted to stop you. I hope you don't mind. But now you can ask me questions about any one of these. Cavity qubit, atom interferometer, quantum entanglement, dark matter, whatever. Okay. Thank you very much for your.
Thanks a lot for this very comprehensive talk. Can I invite Tarun to give the gift first, and then we'll go on to the question answer session.
Oh, I get a gift even before.
Yes, so the gift is right there. Please.
Thank you, Tarun.
Pleasure.
Thank you. What is it?
Book.
The book on RRI.
Selected by RRI.
Thank you very much. Thank you. Take a picture. Okay.
So now
Thank
the floor
you,
is
thank you.
open to questions. And Sumati, did you want to go first?
Yeah, she wanted to ask something at the very beginning, so.
Remember my question, but it was to do with the dark energy,
Yeah.
you know, that part where you're talking about the fact that you can actually measure the potential to measure fluctuations in the dark energy, right? Because lambda, in the ordinary way of thinking about it, is a constant
Yes.
in general relativity. But of course, there are theories from quantum gravity where fluctuations in lambda are predicted.
Are very
So
small.
it is. So what I wanted to ask you is that are these experiments that you have? I mean, how would you know, for example, whether that fluctuation is coming from
Yeah, it's a good
dark
question.
energy and so on? Yeah.
Right. So, you know, so lambda, which is a cosmological constant, some people say that why bother understanding dark energy? It's just a constant of nature. Just accept it and move on. Now, I have this thing that, you know, when Planck's black body radiation, Planck just guessed a shape in 1899, and in order to fit his shape to the black body spectrum, he had to put a fitting parameter, h. So that's why it's called Planck's constant, Planck's parameter. But there was no more significance to that. But then later on, you know, in 2005, in 1905, Einstein said photoelectric effect means light comes in h nu. And then Bohr said in order to explain atomic transition, you have to assume angular momentum to be quantized by h. So all of a sudden, h became a fundamental number. I do not believe lambda. Lambda is just a fitting parameter because we fit the expansion of the universe. We think we cannot do it without having this number, which shows up in the field equation. But if it is something fundamental, then it should appear in some other astrophysical phenomena or some other fundamental processes. So far, we have not seen manifestation of lambda in anything else. So it is probably something that is worth measuring and not necessarily a constant. So there is every reason to be, what do you call it, agnostic about it and say it may have fluctuations. And so we measure this fluctuation by looking at the energy density of dark matter, which is of that order of 12 volt per meter, and its fluctuations. If it fluctuates, then it will affect the atomic interferometry data. It will show up in the interferometric footprint of the atomic beam at the bottom of the thing. And people have estimated to what level of fluctuations you can see.
These are actually experiments.
Yeah.
I'm sort of curious. So I'm with you in the sense.
So we need to team up with theorists to work with us to actually give us estimates of what can we expect from the fundamental physics. Problem is that both gravitational wave and dark energy, there's really no dynamical theory. I mean,
So maybe afterwards I can ask you
yeah,
about
yeah.
experiments because I'd be very curious about
Yes,
that. Because the theory of quantum gravity that I work in, there is a prediction for
Okay, then we-
fluctuations in lambda.
Formula you had this holochrome. I don't remember what it was called, but these two interferometers to measure fluctuations of the, vacuum essentially, right? I mean, there's 10-meter interferometers. In Fermilab, there was this.
That's 100 meter. It's 100
meter? No, this is your atom. That's what he talked about. What I'm saying is, there was attempt to measure something like these fluctuations of holographic fluctuations.
Yeah. The Aaron Chu and
Yeah.
yeah. That was a different experiment. I don't think they had anything conclusive.
Oh, yeah. So
Yeah, there was an experiment. You know this experiment he's talking about? Is the granularity of space-time and fluctuations of. Yeah, this is Aaron Chu and what's his name?
yeah,
The
exactly.
professor
name,
from Chicago.
I couldn't
Chicago,
remember
yeah.
the name, but
Yeah.
this was. I mean, what I'm saying is people do have managed to get a lot of money to set up interferometers and for such quests. I think it's called holographic noise. I think that's the catchword for it. But I mean, the person who got all this done is also very well known. But this name is.
Yeah, yeah, I know. He's originally from Cambridge, but then he came to Chicago. I forget his
Yeah.
name. His name now, yeah. But we would love to collaborate with theoretical people on that, yeah. Sorry.
I have a question from the electron trapped.
Yes.
Very interesting, of course, from the technological perspective. But my question is that the physics you explained about the entanglement between the electron and photon, wouldn't something similar be happening, for example, in a free electron laser, or means where the undulation is happening? You don't know in which phase of the undulatory motion of a free electron
But
laser.
there you are dealing with a macroscopic large number of electrons and photons, so it becomes a classical field. And beyond, when you amplify light to that level, these quantum effects completely wash out. That is why we want to only look at a single electron.
Single.
Yeah.
So just, we're going in a circle here. So very interested in your Cheshire cat experiment, Swapan. So how do you plan to do weak measurements?
That we have to talk about it, yeah.
Yeah, but are you quite confident that they would be weak measurements? Because you're talking about a scenario where...
No, it can be very strong and then you lose all that. Yeah, it's quite possible, yeah.
Yeah, so just to inform you, your other Indian colleagues at RRI have done the first unambiguous Cheshire cat experiment, which is our group.
Yeah.
Yeah, so then, you know...
But
so
this is not with
no, ours is with photons.
It's
of course.
photons.
Yeah,
yes.
yeah.
Photons, right.
I have a question regarding your atom interferometer experiment. So atom interferometer being very sensitive to ambient fields.
Yeah, absolutely.
Yeah, so what is the smoking gun evidence would be if that you can, the detection of dark matter or dark energy, what will be the smoking gun evidence which would differentiate between, you know, effect of other ambient fields on the atom interferometer?
Right, so this is not just a single shot measurement, it's a cumulative. So you get data collected over many, many days, weeks, and so on. And you also have collected data over many, many days and weeks and years and nights and days and seasons from summer. And so you have data on systematic vibrations in that location where you are doing the experiment, where you know the seismic pattern of the wave. So I showed you some data. We could actually look at entire water body of the planet and the solid body sloshing back and forth with a huge peak. Just go back, see if I can an experiment here. There is a, I'll show you that we are measuring all these things. I don't know where, maybe, yeah, right here. Here, yeah, there. See these, so we are measuring a lot of things. These are actually noise, seismic noise and atmospheric Newtonian gradient noise. Atmosphere in the Midwest in Chicago changes, and the column of air that's sitting there actually has a Newtonian noise component. Coriolis force, because it's a rotating system, so the laser is rotating away from the. So all that we're actually studying very systematically over at least 2 years or so. So you have days, nights, weeks, seasons covered. So you have a database of the systematics averaged over 2 years. And then something must stand out above that known systematic fluctuation. If something suddenly happens in one instance, that doesn't bother, because if the earthquake goes on, bang, it goes for 1 hour, but we are averaging over 2 years. So that little blip, it does not matter. So we think we should be able to see with a 1,000-meter drop signature above what is given by the ambient thing, by simulations from computers and stuff like that. 100 meter will be just at the threshold, but it will simply say that it's a good, robust technology. About 1,000 meter actually will show you the real signature. 100 meter is just a proof of principle. Yeah.
So, just like this fluctuation due to thermal thing like this, Nyquist noise or something where the voltage fluctuation is related to the some response function. So in this case, like, do you expect this fluctuation to be related to some kind of response function, or these are completely in the nonlinear regime? Right, like sometimes when you have this fluctuation coming out of, because of thermal this thing, like you have this voltage fluctuation related to the resistance, right? So these things, of course, it's not because of thermal this thing, but this fluctuation, I mean, is it possible that it's also related to some kind of other properties which you can measure instead of measuring the fluctuations?
Oh yeah, sure.
So what kind of those response
atomic
functions
beams
would be?
are used by geologists, and the military is funding professors to build 1 or 2 meter atomic interferometers to see gravitational G fluctuations, which is abnormal, because they believe that we are being spied upon by extraterrestrial intelligence via gravitational waves, which would result in a delta G beyond 10 to the, whatever the standard G is, to 10 to the minus 9 to 10 to the minus 10 G level of shift of gravitational wave. So atomic beams can sense change of G, can sense change of geological, fluctuations. They can sense gravitational waves. They can sense atmospheric fluctuations. Yeah.
Yeah. No, my question is that is this fluctuation is also related to some other macroscopic quantities, like the way you see it in thermal system, like for example, voltage fluctuation is related to resistance.
Not can I say that. You can repeat the question again. I didn't.
Yeah, like suppose you have a circuit and then
Yes.
you look at the voltage fluctuation because of the thermal
Nyquist.
Nyquist noise,
yeah.
right? So this fluctuation is related to the some kind of dissipation in the system, right? You
Yeah.
have a fluctuation dissipation.
Yeah.
So is there a similar fluctuation dissipation
For gravitational.
for gravitational or black?
So So I am working with, some people believe in inflationary cosmology. It says the space-time inflated faster than speed of light for the first very beginning of the universe. So there's a bunch of theoretical physicists working, applying fluctuation dissipation theorem, knowing the rate of expansion of space-time at the beginning of the universe gives you the dissipation part of the fluctuation dissipation theorem. So that should set a scale for what kind of space-time fluctuations you should expect from the Big Bang. So we are working with those theoreticians to actually see what do we expect from it, but from very general principles of different models of fluctuation and so on. Yes.
So what selects this frequency band for atom interferometric
So
approach?
that was, let me show you the bandwidth. It was like 10 hertz down to about millihertz or something like that.
Yeah, no. So how, like what sets that? Why are atomic interferometers sensitive to that wave band?
This is actually you couple the wave and you see what kind of, where is that? I'm trying to get that diagram. Okay, let's just stick here. So you have to couple the fluctuation of space-time metric to what the atom actually, given a certain atom, let's say strontium, and you look at its energy levels, and you see how they could shift their phase by dropping a certain distance.
Right, but that is fixed, right? In the sense that an atom in a gravitational field, given the gravitational field, will have that imprinted on the change in the levels, right? And then if that
change of the phase,
right,
of the phase of the system, right? It changes the phase of the atomic energy levels.
Okay, so I'm missing something here. But so what sets the fact that you are sensitive between millihertz to hertz?
That depends on the coupling of the gravitational wave to the atomic wave function. And if you have a space-time fluctuation that is at that frequency, okay, then that,
Okay.
okay, so that will make the phase fluctuate between the atom that is correlated to that frequency.
Yeah. So
And so you have to be able to measure that phase fluctuation in the atomic beam, and that frequency range tells you that it gives you the limit of what you can observe in the atomic quantum wave function phase fluctuation.
Right.
So the instruments that are used for atomic phase fluctuation measurements are limited
Okay.
to that, which maps into that frequency.
I see. So if I wanted to use this technique
For very low or very
high, then what do I need to change?
you have to change
The atomic system?
yeah, you have to change the atomic system. Yes, exactly. Either use a totally different atom that does not exist,
Okay.
or you use the same atoms with the known energy levels, but you have to understand how to measure very, very small or very, very large phase shifts now.
Also, the slides that you're showing with these measurements of microseismic peak, and that's very interesting because we have been doing.
Is it the sensitivity plot?
Yeah, those. No, you showed those microseismic peak coming and all the measurements that you did with matches, right? All the
Oh, yeah.
gradient noise and stuff
Yeah,
like that.
you
Yeah.
see that's the estimated sensitivity, right? That's what you just.
No, those bands that were there, right? I mean, of
Let me
excursion.
just see. Hold on. Is this the one you're talking about?
No.
This?
The data that you had on the, which showed the noise, yeah, noise. Seismic noise, yeah.
Okay. Is it was after this? Must be after this. No. Yeah. Let's see this. Yeah. Okay.
Yeah, this one. So this is from your experiment?
Yeah.
Yeah.
This
So-
this is a laser. So you have a laser that is going 100 meters. So the wavefront gets distorted by particles of light, dust, even though it's a very high 10 to the minus 10 vacuum, but still the wavefront has to interact with the cloud. And so any slight distortion of the wavefront will change the atomic phase that's interacting with it. So we have to know that. So this is actually how do you compensate for the laser wavefront. So the most of the atoms in the cold atom cloud do not see too much of a deviation of the phase. So these are all feedback systems to keep the laser wavefront constant. And this is just measurement of the seismic noise and gravitational noise at the bottom of the 100-meter shaft, in the middle, and on the top.
These are with other seismometers, or
Yeah,
this is? Oh,
or gravimeters, whatever you call it.
Okay.
Yeah, right. Accelerometers.
yeah.
Yeah,
So
right.
that's.
And this is a big peak. I was telling you, just
Yeah.
surprised is the peak of the entire Earth flushing back
Yeah.
and
So
forth.
this is the I mean, we needed to characterize this for all the sites.
You
here,
must
so-
know some live.
Yeah. So
That's right.
I was curious whether you could do it. with
These are
the
all
top.
little tiny seismic earthquakes happening everywhere. Hey, speak on the microphone.
You're hoping to increase the sensitivity by increasing the length of these columns, is it? I mean, that's the idea?
Yeah.
That you would increase the sensitivity
Yes.
by increasing the length of the
Length of
columns.
the thing. Yes. Because
Okay. So these are just for the 100
yeah,
meter.
it's just linear relationship with the phase changing with length. That's all. Nothing more than that. Yeah. Hi, Sadiq.
Yeah, so just to ask, if you had a network of clocks as opposed to a network of, this interferometers in mine shafts, what is the relative playoff between a network of precision clocks versus the interferometers? Which is advantageous? Because both would be good
Yeah,
enough
I
for
think
this.
it would
It
be-
doesn't matter whether you
No,
do time or
if you had a
space.
good clocks and if you had a network of clocks, that would work.
So why are we doing this and not that, or even that's being done separately?
I don't know whether anybody is proposing a network of clocks. Do you know anybody? No? It will have to be a very
Yeah, but then if you want to go to millisecond pulsar timing, then there was no need to build the LIGO in the first place.
How many of you are students here? How many are students? We are all students, I know, but how many are real students? Oh wow, they are all in the back. And no questions from you guys? All the experts are asking questions. Come on, somebody.
Maybe they can ask you what he's going to know more informed. So if that is good, then we can end this formal session and thank you once again for this very nice seminar.
Thank you guys, thank you.